Let us discuss derivatives of Stirling's formula. We have Stirling's formula as obtained as this equation, and here when we will take derivative on both sides with respect to variable n, because x naught and h are fixed, on differentiation we will have LHS becoming f dash of a plus nh multiplied to h, and in the RHS we have derivative of y naught with respect to n will be 0 because y naught is a constant. Derivative of this term with respect to n will be delta y naught plus delta y minus 1 divided by 2 because derivative of n with respect to n will be 1. When you consider derivative of this term, you will get 2n divided by 2 factorial multiplied to delta square y minus 1, which becomes n times delta square y minus 1. For this term, we will have to make use of product rule for differentiation because there are two terms n into n square minus 1 which involve n. Otherwise, you can expand n into n square minus 1 as n cube minus n and then take derivative, which will give you 3n square minus 1 divided by 3 factorial multiplied to this constant term. Similarly, derivatives of other terms can also be evaluated. Thus, we will arrive at equation 2. In equation 2, when you will give n equals 0 on both LHS and RHS, you will get f dash of a plus nh equals f dash of a, which equals 1 by h times delta y naught plus delta y minus 1 divided by 2 minus delta cube y minus 1 plus delta cube y minus 2 divided by 12 plus etc. When you give n equals 0 in equation 2, only terms containing powers of delta, which are odd powers, will only remain as non-zero terms. This equation can be used whenever we have the special case n equals 0. In order to find out second derivative of Stirling's formula, it's enough to take derivative of equation 2 with respect to n. On differentiating both sides of equation 2 with respect to n, we will arrive at this formula. Here when you give the special case n equals 0, you will get f double dash of a plus nh equals f double dash of a equals 1 by h square times delta square y negative 1 minus 1 by 12 times delta raised to 4 y minus 2 plus 1 by 90 delta raised to 6 y minus 3 minus etc. Notice that when you give n equals 0 in this formula, only terms of RHS involving even powers of delta will remain non-zero. This formula is applicable whenever we consider the special case n equals 0 and we have to evaluate second derivative of Stirling's formula. At the particular case n equals 0.